Alright. So our last topic we're going to have a look at is a tiny bit of quantum mechanics, but nothing too difficult. So in the previous lesson you saw that we can think of light as being made of small photon particles. Okay, write this down. You got this?
Mm-hmm.
Yeah. Yeah. You don't need to write this down. I want you to notice an analogy here. So you recall from fields that the force between the moon and the earth can be found by using this formula. F equals G m1 m2 over r squared. Yes? Now if you look at the hydrogen atom, you have proton, electron, and you have a very similar looking formula, don't you? So the situation looks the same. There's not much of a difference except for scale. Earth, moon, a force as G m1 m2 over r squared. Proton, electron, a force as K q1 q2 over r squared. A constant 1 over 4 pi epsilon 0. I lied earlier when I told you that the distance has a minimum. I said after meter, centimeter, centimeter, millimeter, millimeter, micrometer, micrometer, nanometer, forever. I lied. This is not actually true. There is a minimum distance that you can have, and you can't have less than this. Okay? So you don't notice this on a day-to-day life. On a day-to-day life, you don't notice that there is such a thing as a minimum distance, because it seems like every distance is possible. However, when you look at an electron and a photon, you do notice that there are only certain distances the electron can be at, and it cannot be in between these distances. So this is like a quantum of distance. There is a minimum distance, and the electron can be at these distances, but not in between. Lorraine will do this with you in chemistry as well. Her analogy is like stairs. You can be on one step or another step, but you can't be in between the steps or you'll fall. It's unstable. Likewise, you can be at one distance or a second distance, but not in between. Do you understand what I'm saying? That there are minimum possible distances. And we can kind of see this as well when we have situations like this. Okay, so if you had pure white light and you put the white light through a prism, you'll get all the colours of the rainbow. Okay? If you have a hot gas, just a gas that's really, really hot, like the sun. The sun is a hot gas. Hydrogen and helium, it's very hot. And you put this light through a prism, you don't get a colour of rainbows. Do you notice that it's mostly black except for a few frequencies, a few colours? And likewise, if you had a cold gas and you shine a light through the cold glass and then through a prism, again you don't get a rainbow. What's happening here? There's some colours missing. Yeah? Now there is a reason for this. This is the continuous spectrum. This is all the possible colours. Red, orange, yellow, green, blue, indigo, violet. This is called the emission spectrum. These are the colours you get from the sun, for example. Okay? Now if you notice, look here, what colours do I get? I get a red and an orange, but I also get some other colours as well. But these are the colours we notice with our eyes, red and orange. But we don't get all possible colours from the sun. We only get some colours.
Do you get pure colour from the sun?
Yeah. This is like violet, ultraviolet. It's the one that gives you cancer. Skin cancer. It's not, the red and the orange light from the sun is not the one that hurts your skin. It's the higher frequencies, the violet colours that give you the skin damage.
It's kind of like the most useful one. It's very, very useful.
Useful for what though?
For vitamin D, like for everything. Yeah, for vitamin D.
You need high frequency for your body, but not too high.
Which I can get it like what's the evening?
Oh, I know what you mean. I'm not sure actually. Now, the absorption spectrum. So what happens here is you take some pure white light and you shine it through a cold gas. You know, like for example, I have some helium. Helium doesn't glow, right? You can't see helium, can you? You can't. It's like air. You don't see it, yeah? It's not glowing. So if you have some helium in like a glass container, and if you shine a light through it, and then put the light through a prism, you notice you don't get this anymore. Some of the colours are now missing. Yeah? This one is called an absorption spectrum. And I'll explain what's happening in a minute, but I would like you to try and at least write something, or even draw this if you can. The tree. You can write it, KJ, if you want. Yeah.
What's the first spectrum?
Continuous spectrum.
The second?
Emission spectrum.
The last?
Absorption spectrum. You got this?
The last one.
Okay, you got that? Yeah. So the reason I'm showing you this is actually this is part of the evidence for the different distances that are possible for the electron. But we'll explain why that is now more in a moment. So, if you look here, pen again. Right, so here is, for example, the nucleus, protons and neutrons. Here is one distance the electron can be at, and here's another distance here. Do you remember that there's a formula for the potential energy when you have this electromagnetic force? Do you remember it? It's something like PE equals minus K. Do you remember this?
What's for?
The potential energy between, never mind. You see, you're not doing revision, which means I can't reference things that you've done recently.
No, it's not really.
The formula for the potential energy for an electron that's from a proton, from its electric field, minus K, no, Q1, Q2 over R, wasn't it?
R squared.
No, that's the force.
So Q E E. Okay, it's only one Q, not two Q.
Yeah. Cora, don't pretend you knew this. Did you know this? You weren't saying it when I asked you. Anyways, my point is that the potential energy is negative, and what happens when the distance is greater?
More negative.
No, less. Because if it's a bigger distance in the denominator, it's small. The denominator is bigger, so in total it's smaller. So anyways, my point is here the potential energy, we'll call it PE2, is negative, and here PE1 is also negative. Which is more negative?
P2.
This one.
P1, yeah.
This is more negative than this one. So actually it means that this one here is bigger than this one. Okay? Now. No. Okay. Now, if the electron moves from here up to here, does it gain or does it lose energy? It gains energy. It has more energy. Right? So the only way to make the electron do this is if you give it energy, usually in the form of a photon. So what happens is a photon comes along, it hits the electron, and the electron moves in a higher orbit. You've done orbits with Lorraine in chemistry, the electron orbits, yeah? So what happens when the photon hits the electron gets more energy and it moves up. However, if it does not get enough energy from the photon, it will not move halfway up. Because can it be in between these two? No. I said these are the only possible distance. So what do you think happens? Well, nothing happens. The electron doesn't take the photon because it doesn't give it enough energy to move up. So instead, just nothing happens. It doesn't absorb the photon. But if this photon has enough energy, the electron will take it and move up to the higher orbit. This is the reason why there are some gaps in the colour spectrum. What's happening is when you have your gas and when the light comes in, the reason there are some colours missing is because these colours have the frequencies the electron wants to move up to the higher orbit. The colours that have a lower frequency than what it wants, the electron won't take it because it can't use it to move to the next orbit. So this is why there are gaps in the colour spectrum. So this is what's happening. And likewise, when an electron is in a higher orbit and it moves to a lower orbit, does it gain or does it lose energy? What's that? It loses energy. So the conservation of energy says that this energy is not gone, but changed. What do you think it's converted into? No. It's converted into a photon of light. So when the electron falls from the higher orbit to the lower orbit, a photon is released. So when it goes from a high to a low orbit, a photon comes out. But when it goes from a low to a high orbit, this is because a photon came in. So if an electron falls from high to low, what happens? A photon is released. If an electron moves from a low to a high orbit, it's because it received the photon with enough energy. It absorbed the photon and rises to the higher orbit. Okay, so let's have a look at this as an example. You have an electron, and it's in energy state number 4, and it moves to energy state number 3. So I'll draw that for you. What's happening here? Here's the nucleus. You have orbit energy level 1, 2, 3, and 4. And in this example, the electron moves from 4 to 3. So the electron is here, and then it moves to 3. So what happens? Does it gain or lose energy? It loses energy, and this energy is converted into a photon of light. So what I want you to do is, what is the energy of the released photon? Well, how much energy will this photon have? How can I find that? Yeah, it'll be the difference between these two. That's how much energy the photon will have. Because basically E4 should equal E3 plus the energy of the photon. Conservation of energy. So the answer is just the difference between these two. So the difference is 0.66 electron volts. So the photon will have 0.66 electron volts. Can you convert that into joules? And tell me what you get.
1.056 times 10 to the minus 8, minus 19.
Joules. This is how much energy that photon will have. Yep. Conservation of energy, that's all it is. Next one. Right, so this one's a bit more interesting. You have the electron, and it's in the ground state. This means it's in the lowest possible orbit. It gets a photon and then jumps up to the third state. So what's happened to its energy as it goes from this to this? I'm sorry, that's in electron volts. I should have said that for both. So if it goes from minus 13.6 to minus 1.51, what's happened to its energy? It's gained energy. Where did it get this energy from? From where? The photon. So my question is, tell me the frequency of the photon. Do you know how much energy this photon must have? Yeah, how do you get that? The subtraction of the two. Do you have a formula to get the frequency of a photon if you know its energy? Yeah, it's the first formula I gave you, isn't it? E equals HF. So I want you to calculate the F. Do you need to convert the energy into joules?
Yes.
Okay, so let's see what we get. Have you got an answer, KJ? Shouldn't take too long to do.
2.9 times 10 power 50.
Correct. KJ, did you get an answer?
Yeah, 2.9 times
Yeah.
10 to minus.
So,
Like 10 the power.
power 15. Right. So Tekken, what did we say the energy was in the lowest state? It was minus
13.2.
electron volts. And the energy in the higher orbit of, what was it, E3, was it?
Yeah, minus 1.51.
So the difference here, it gained 12.09 electron volts. If you convert that into joules, what do you get?
1.9 times 10 power minus 18.
Joules. Where did it get this energy from? From the photon. What's the formula for the energy of a photon?
HF.
HF. must equal this. So if you divide this by h, you get the frequency is 2.9 times 10 to the 15 hertz. Yeah? Okay, continue. This is a normal question for the exam. You can watch those videos anyways.
deBroglie.
Yeah. Now,
I knew that thing.
you know this dude? We said light behaves like a particle, that you can think of light as being made of photons, little bits of light particles, yes? In fact, deBroglie said an electron can also behave like a wave as well. That an electron can sometimes look like it's behaving like a wave. Now, if you want to know more about this, I recommend you talk to the January students, because the January students had an active listening lesson on this topic. So if you want to know why or how an electron can behave like a wave, talk to them. Grace, Amanda, Sophie. But for us, we'll just say an electron can act like a wave. Now, in fact, for the syllabus and for the exam, they barely ask you to do anything with this, except for saying that if an electron behaves like a wave, what would be the wavelength of the wave it's behaving like? But unfortunately, I don't think so anyways. If I just double check the syllabus here.
What's P?
Momentum, which I'll get to just in one moment, okay? NCUK. So what I mean by an electron behaving like a wave, well, I'll get to that in one sec. Yeah, you see, the syllabus just asks you to use this formula, but it doesn't say explain or understand what this wave means or represents. So I don't like saying it, but really for the exam, the only type of question you could get here is what is the wavelength of an electron, and you have to use this formula. Now, you might be wondering, and you should be wondering, what wave are we talking about when we say the wave of an electron? Because isn't an electron a wave? No, it's not. What's an electron? It's just a little particle, isn't it? So you should be thinking, what on earth does it mean to say the wavelength of an electron? Because an electron's not a wave, it's a particle. And unfortunately, well, not unfortunately for you, because this means there's less things for you to know for the exam, but unfortunately it's not really part of the course to say exactly what this is. However, I did do an active listening on it, so the January students actually know what I'm talking about when I say the wavelength of an electron. So I do encourage you to talk to them about it if you want to. But for the exam, the only question that they could ask you is calculate the wavelength of an electron. And you get it from this formula, where P is momentum. So what's the formula for momentum? mv. So here is an example question that maybe will help you understand what we mean by wavelength. But can you just write this formula down, H over P?
H is still constant.
It's still the constant, yeah. Okay, got that? Now it's not just an electron, but it's usually an electron. it doesn't really make sense to do it for a proton or neutron, because although it does have a wave, the wave, you can't really see the effect of the wave. The next example will help to explain more the idea. Can I go on?
Yes.
Okay. So what on earth am I talking about when I say a wave of an electron? So what we have here in this example is, we go back to, remember the experiment in the wave section where we have the double slit. Do you remember this? And what image do you get on the screen? You get different dark and light spots. Do you remember this? So there'll be a spot here, and this is n equals 0, and then there'll be one here, 1, 2, n equals -1, n equals -2. And this happens when you have a wave. Do you remember what this topic is called? This is the interference pattern. Diffraction, yeah, and so on. Interestingly, you get the same pattern when you use an electron. But an electron is not a wave. So how come we get this wave pattern here? Like I said, talk to the January students. But the point is, if you use electrons, the electrons will behave like a wave. So in quotation marks here, like a wave. So some electrons land here, some here, and so on.
Don't some bounce back?
And some bounce back, of course, as well. So the speed of the electrons here is 0.1 the speed of light. And the screen is 1 meter away. So my first question, which I want you to calculate, is this electron is behaving like a wave. What is its wavelength? So use the formula, please, previously. It's on the calculator as constant number 3. Look up in your notebooks if you don't know it. You got that? Yes? Tekken, what did you get? Okay. Where's your calculator for
I forgot.
oh, goodness sake.
1.3 times 10 power minus 2.
C is 10 to the 8, isn't it? Yeah. No, I got 7.27 times 10 to the minus 11. I got 0.0727 nanometers. Wavelength is 0.0727 nanometers. You didn't get this? What did you get? KJ, what did you get?
2.4 times 10 minus 39.
Goodness sake, guys, come on, you're just using your calculator. So what's the formula for the wavelength? H over mv, like this. Okay, so what's the value for H?
6.626 times 10 to the minus 34.
And what's the value for the mass of an electron? No, that's the charge. The mass is 9.11 times 10 to the minus 31, and the V is 0.1 times 10 to the 8. So what do we get? Type this in.
What is 0.1 times 10 to the power? 0.16 to 0.1 times
3, sorry, times 3. Thank you.
Why did you get this formula from? 72 points.
The formula, Karar, is the one that's in front of your face 1 minute ago. H over P.
But here H over MV.
But P is momentum. What's momentum?
That's times.
Yes, MV. Alright, so what do you get here? Sorry, Tekken. Maybe this is what you said a moment ago. 2.42. Is it?
Yes.
Is it? You said minus 39.
Yeah, that's the only thing.
Oh, that's the only thing. It was like 28 orders of magnitude wrong. That's the only thing.
One, you said 7.
No.
I forgot to put my
Stop
one.
talking, please. Stop talking. Stop talking. Right, 10. Right, so this comes in at 0.0242 nanometers. Yes?
Yes.
Okay, great. Do you have this written down?
Yes.
So the next part, these electrons, okay, so what I'm telling you now, here, that the distance here is 10 to the minus 10.
Between the two of them.
What the heck? Alright, fair enough. The distance here is 10 to the minus 10 meters. Yes? So do you remember the formula to get the separation distance here?
D over...
Yeah. Lambda equals, these we'll call, we call this distance here D, and this one here is D, and this one here is F. Isn't it? Yeah, so what's the formula for the lambda, do you remember?
D over... D sine theta over...
No, the other one. Look in your notebook. Yeah, S roughly
equal to
lambda.
D times lambda times D over D.
Which, big or small?
Numerator is D.
Like this. Yeah? Right, so what I want you to do now, oh, that's actually part C. Can you calculate what this S is? So it's 24 centimeters when you type the numbers in. This is the answer we just worked out. This is 1 meter, and this is 10 to the minus 10. Okay, the last part here. So the last thing I want you to do here is get the angle for the first one. So I know you remember this formula. What is it?
D sine for
N lambda equals
D
d
sine.
sine theta. So what's the n for the first one?
1.
Yes. The lambda, do we know it?
Yes, 0.07.
Yeah. And the d?
Yes.
10 minus 10. So get me the theta.
Yes,
46.6. Yeah. But again, what am I using here? This is from waves. You know? So like if you think about it, this lesson used the formula from waves and conservation of energy formula for the calculations for the photons. You know, this is what I mean by it's important to do your revision from semester 1 because we use the same formula still. Yeah? Okay? Okay. Write that down, please, or take a picture. Okay, you got this? Yeah. So look, I'll be honest with you. I don't think many of you are ready for the test, and I think many of you have left your revision too late. And that's just simply the way it is. And that's a choice that you made by not doing enough revision. So if you want any chance of doing well, you're going to have to work really, really hard. And some of you I don't think will do this. And that's just reality. So all I'm going to tell you now is we're going to start the revision on Monday. And if you want any chance of doing well, you should be doing your revision now, and you should not have waited until this Monday to start doing it. So I want you to we'll have maths tomorrow or physics? Maths. Yeah. So anyways, for class on Monday, if you want to bring your laptop or your iPad or whatever, because we'll be looking at physics papers, okay? I'm going to upload some more papers maybe over the weekend, I don't know. On Moodle. Because I have more papers. So I'll start with the most recent paper I have and work backwards through time. Yeah? But also don't forget to do these homework, so I'll do them in the first class on Monday morning. For whoever decides to show up at 9.